Hi, I'm Zach Landis-Lewis. I'm faculty in the Department of Learning Health Sciences at the University of Michigan Medical School. To successfully mobilize CBK, we need methods and resources that can help people efficiently understand the purpose and functions of these models, especially when larger collections of models are being implemented, for example, in knowledge bases. Vignettes are a kind of software documentation that people create in the R statistical package community to provide tutorials for our users. And vignettes can make complex software easier to understand by providing examples of data and analyses with supporting discussion and interpretation. As far as we know, a practice like that of developing vignettes for CBK has not been widely adopted, but it might benefit CBK developers, implementers, and other stakeholders to promote better learning for CBK mobilization. We developed vignettes for CBK in a knowledge base for a precision feedback system that generates emails like this one to anesthesia providers and which can enhance the messages and communication in clinical quality dashboards and feedback reports. So our system selects high-value messages about care quality based on theories of motivation and preferences of feedback recipients. We have a knowledge base that this system uses containing logic models, ontologies, a knowledge graph, and algorithms that interact through a software pipeline, which we've implemented in a web service. We've written these vignettes and made them publicly available in our GitHub repository. We created 10 vignettes that illustrate how two different clinicians with different performance data and different preferences end up receiving different feedback messages through the processing of their data by the precision feedback system. So the vignettes describe this process in kind of a story, walking through each analysis that the system conducts, and it links to other resources such as ontology terms and classes in BioPortal, as well as details about performance measures for care quality. So for these 10 vignettes, while we set out to improve the transparency and findability of our knowledge base for external stakeholders, we ended up realizing there's several benefits for our own team, including improving our own communication and learning, supporting our project management, and most recently, we're using them to test the performance of our system. And you can see these vignettes if you follow this QR code. Thank you for your time.
Hi, I'm Simon Schuster from the University of Melbourne. I'll quickly work through how we approach evidence synthesis automation. So to provide some context first, let's have a look at evidence-based medicine and how it views the distribution of information. So it is based on the premise that quality and quantity of evidence differ and can be represented in a pyramid. So ideally, clinicians would always make decisions based on the knowledge available at the top of the pyramid. This is where evidence that has been filtered and synthesized is available. The top level builds on lower levels of evidence, such as different kinds of trials. It summarizes that information and critically evaluates it. The problem of the top of the evidence pyramid, though, is that this information is rarely up to date. So the process to construct a systematic review, for example, is very complex and time-consuming. The goal of our research is to work towards solutions to having up-to-date synthesized information more readily available, specifically in systematic reviews. We therefore develop automated approaches to systematic reviewing that could complement human reviewers in their work. Let me now zoom in briefly on one such area, namely automated quality assessment of evidence. In recent work, we studied in detail two tasks, one of assigning quality grades to larger bodies of evidence following the grade framework, which is shown in the upper half of the slide. The other approach concerns risk of bias assessment for individual randomized controlled trials using different bias criteria. For both grade and risk of bias assessment, the ground truth quality judgments come from the Cochrane library. In the first stages of our work, we identify and extract parts of reviews that would serve as useful predictors in our models. So this can be structured data obtained from tables and summaries of findings, or they can be free text. The data extraction step results in a computer-readable data collection that enables machine learning. We use a neural model that finally predicts a quality score. So in addition to data and model development, as well as studying models' predictive performance, we investigate several other aspects of performance that we think are critical from the point of view of practical applications. First, the questions of disparity and fairness. Are model predictions equally good on subgroups of data, such as medical areas? Can algorithmic bias be mitigated so that the resulting models are fairer? Secondly, we would like our classifiers to be well calibrated, meaning that the confidence estimates of their predictions are aligned with empirical likelihood of the model being correct. Thirdly, a related concept is selective classification, where we accept the classifier to have lower coverage in order to obtain more accurate predictions. In this way, the most accurate predictions would require less or no oversight by humans, whereas the least accurate ones would need human reassessment. So in summary, our work strives to make synthesized evidence more accessible and current through automated methods that would complement human reviewers. Thank you.
Thank you for joining me for this talk. My name is Ruth Carlisle, and I'm part of a small national team overseeing the quality assurance and development of knowledge and library services across organisations in England. If we're thinking about computable biomedical knowledge, it can provide personalised information, but it's only of value if actually people have the digital literacy and the connectivity to access the information. And also when they've accessed it, they have the health literacy skills to be able to assess it, understand it, and use it. In England, 43% of adults struggle with words-related health information. As soon as you add numbers, 61% of adults aged 16 to 65 struggle to understand that health information. And as we know, most health information includes numbers as well as words, such as vital details on the number of tablets. Working with the University of Southampton, we reanalysed existing data sets to identify localities with poor digital access, which are identified in blue on the map, but also areas where there's likely to be poor health literacy, identified in red. And we looked at the range in terms of people's experience and their health literacy confidence, and found that actually it ranges from 46% of people struggling with health information that involves both words and numbers to a staggering 82%. So we know the national challenge, and we've identified the localities in which it's a particular issue. What are we actually doing about it? Well, we wanted to make sure that we were taking an approach that was not just about projects and short-termism, but sustainable change. So we've integrated activity with knowledge and library services in the community. Libraries and community information services are ideal partners. In the UK, 93% of the public trust librarians, second only to trust nurses and higher than their trust of either doctors or teachers. Public libraries act as digital hubs in areas with low digital connectivity, as well as helping people to share digital skills. We're working as part of a national strategic partnership with our national body for librarians, which is the Chartered Institute of Library and Information Professionals, Libraries Connected, which oversees public libraries, and also Arts Council England. We cascade training, share resources, and test approaches and pilot sites. In terms of our approach, we needed to make sure that actually we were sharing resources in ways that made the most of what already exists. So our reviewed resources are available through a toolkit, but we also worked in partnership to develop e-learning, training, easy read resources, and compilations of resources that others can use for the public. So as you think about your own next steps at the end of the conference, I'd welcome your checking of what data you already hold and what implications that has for targeting. Perhaps actually thinking about staff confidence and whether or not you could use health literacy tools such as our e-learning and toolkits, and also signposting to high quality health information to increase the trust amongst members of the public. Thank you for your attention, and I look forward to your questions.
Hello, I'm Hannah, a knowledge specialist at NHS England, Workforce Transformation and Education within the wider knowledge and library teams. I'll quickly walk through how I generate search strategies using GPT-4, but this will also work with BARD and similar large language models. I get asked to search for healthcare topics a lot, so I set up a thread for generating search strategies that use Boolean and/or terms. I just paste or type in the clinical query, and GPT-4 will generate a search strategy for me. I prompted it to avoid Google search operators because GPT-4 doesn't use them very well. But it can be prompted to expand the search to include other synonyms if required. As you can see, my question around the effectiveness for people with depression or anxiety has been broken down into a Google search strategy, which can also be used in Google Scholar as well. I found that keeping search strategies fairly short and simple gets the best results for Google. For more advanced search databases like Medline, I have a thread set up for the generation of larger search strategies. So using the same clinical query as before, I generated a search for each aspect of the question, so depression or anxiety, and then clinical effectiveness, and then exercise. They have their own lines in the search, so I can keep an eye on the number of results for each line. I could also add medical subject headings in there too. GPT-4 and BARD will try and generate medical subject headings, but unsuccessfully, so they won't really work. But this can be avoided by prompting tools to not use mesh and other search operators outside of the usual Boolean and/or. And of course, it's important to be aware of bias, both of the user and the tool when building these search strategies. And large language models can be prompted to use both British and American English, but it will generally default to American spelling unless prompted otherwise. And it's good to double check the strategy for hallucination, either for unusable search operators or irrelevant keywords. For better results, it's generally best to consult with knowledge and library colleagues if you are fortunate enough to have them. I recommend testing these tools with various different queries. The more broad the query is, the better the results in my experience. And that's that. Thank you for your time.